estimation of parameters. And there will be primarily two parameters that we will be interested in. One is the mean, and it can arise as the mean of a single random variable. It can arise as the difference of the mean of two random variables. And you know that the difference of the mean of two random variables is this. And finally, we may want to estimate the variance or the standard deviation of a random variable. Actually, we do the variance. And if we estimate the variance, then we estimate the standard deviation because we take the square root of the variance. Easy enough. What are the assumptions? For here, always x. X is what we call population. So think of x as population. It's the underlying random variable. And when we talk about the underlying random variable, you ought to define it at the beginning of the problem. You have to say, this is the random variable I want to talk about, of whom the parameter I want to estimate. Then locate the parameter you want to estimate, identify it. And if you have to deal with two random variables, x and y, then you have to identify both x and y. Okay, that's critical. And always open up your book or your formula kit, and this is what I will be doing from now on. I'm not going to write the formulas down. You have them here. What I want to let you to make you understand today is which formula you want to use. Of course, estimation of proportions is again essentially estimation of a mean, and that's the mean of a Bernoulli random variable. So estimation of a proportion is estimation of a mean, but this time x is a Bernoulli random variable. Is a Bernoulli, okay? That's what, that's basically the setting. Now let me go here to my book, and that's a nice book. I have databases here. And okay, now I need to go to the next page. So I need to go down here. And let me I guess I'm trying to see how I can this thing doesn't seem to be. Let's resume. So this is let me read this set here. Although this is although we need a woman, this talks about men, right? Because women don't have a prostate, but they may work, you know. Indicators of prostate biopsy results. You know that prostates are kind of difficult for men, because after a while the prostates tend to enlarge, and one of the very big problems is that you got to run to the bathroom. You've seen it in commercials a lot. And it becomes pressing sometimes. You need to go right now. And you can kill to go right now sometimes. That's because the prostate is really, you gotta fit too many things in the abdominal cavity. And it's sitting right under the bladder. So essentially when it gets enlarged, it can also split the bladder in two parts, one that can be flushed out and the other that cannot. And that's when we have a very serious condition. We have to put a catheter. Now, the enlargement of the prostate in most cases is benign, but in other cases is not benign. It can be cancerous. But in general, urinary system cancers have a slow progression, even in young ages, and they tend to stay in the organ. Primarily, prostate cancer for older people tends to stay in the organ for way too long. That's why sometimes we don't even do an intervention if it's not needed. So here we have a data set which is fairly big. It comes from 301 male patients. And we want to see if they have exhibited one of several reasons to suspect declining health of their prostate glands, Okay? These data set were recorded for the patients in the order they were presented. These data sets have the advantage that they include biopsy outcomes, regardless of the results of preliminary examinations, false negative results, who have negative biopsy outcomes when a tumor is present, we have false positive results, positive biopsy outcomes when no tumor is present. So we have several data for these people who have AIDS, digital rectal examination result, which I guess you all understand what that is, and transurethral ultrasound result, where basically you go close to the prostate and you try to see the abnormality of the shape. Abnormality of shape of the prostate is a good indicator that something's wrong there, but then that thing might be benign. There are benign abnormalities of shape, but it's not as much. Roughness of shape is a good indicator that you have a malignancy. And then after you have the malignancy, you have to do fine needle aspiration, which you can do again going through the colon, that route, because the colon really touches the prostate. So we have 301 patients. Mean age is 66.76. So what do you see in this study? I want you to understand what we see here. We have PSA. PSA is prostate antigen. It's a cancer. It can be related to cancer. Elevated levels of PSA may be related to cancer, but they're not very specific, in a sense that elevated PSA levels can identify you, can single you out for prostate cancer, but you cannot diagnose prostate cancer just by elevated PSA levels. They can be elevated for other reasons as well. The other is the volume of the prostate, which we can measure accurately with the ultrasound. And the last is the PSA-D. It's a more specific antigen related to cancer. So let's see these things. 301 people were examined. So what does that mean? What do we mean by mean there? 66.76. What does this refer to? The average. Average. What average? Age. Age of where? Where? Which patients? Every patient? Just these patients. Just these patients. So how do we call it specifically, this number? It's a sample average. It's the sample average of their age. So if here in the first column, what is the underlying random variable? Age. Age of what? Or age of whom? Age of my age? Your age? What is? More specifically, I want more accurate description. Verbal description. It's the age, that's the random variable, which says age of men that participated in the sample. Okay? So this is what we have here. And then we say PSA. PSA of men is, that was again, we get a mean and we get a standard deviation. Notice that the standard deviation is fairly big, okay? You see that something here which is qualitative of the big variability. Standard deviation for the PSA is 16.91 and the mean is 8.79. So you see that the standard deviation even allows for negative concentration, which of course they can't be. That's indicative of the very big variability we can have in this. And the same also is true for PS8. Now, for patients 11 to 301, and actually I'm going to go a little bit down to see, because you can't see the second part of the data set, which is actually I want you to see. Oh, I think I need to hook up my mouse real quick to make this work better. So here are our patients, and that's the one. That's a table I want you to see. So here you have 10 patients. Actually, the entire database contains, of course, many more, and they have done all of those. They identify all of these things for all of them. So biopsy results here, you see that several had 0 means negative result, 1 means positive result. Transurethral ultrasound is essentially something that you perform or you did not perform. Digital rectal examination, you performed it or you did not perform it. And here are the PSA levels. And here the volume, the prostate volume. Now, if I ask you, and that's essentially a sample of the data that exists here. What I can go back and ask is the following. If I look at these more descriptive sets here, these more descriptive sets, I would like to ask the following. For people who look here, there are too many data sets for the reader to do calculations with a computer. Now, 296 patients, and you see them here, this line, were at risk for prostate cancer. Okay, and 5 patients were excluded for that. So for 296, we do have indicators that they may have prostate cancer. Then, what is it possible to say about, for example, one question would be, what would be the average, what would be the mean of their PSA? Can we conclude anything from the mean of for the PSA, from the PSA values that we have? Can we say anything about that? Now, out of the 301 patients, you see PSA values are essentially dominant here, and that's why they look to be almost the same, because these you have 296 patients identified for risk, for high risk for cancer, for prostate cancer, and they are among 301 patients. So the 301 patients is basically essentially this that we have down here. 5 were excluded. Why? Because there was no homogeneity. They would actually have corrupted the sample. It says, the problem says, here the data set, the description says that 5 of them had severe benign prostatitis. So they are not, once it's identified as benign, there's no cancer. That's why they have been taken out of the sample. So if I use this data sets here to form the following problem, what is the mean? If I say X, let me phrase it differently. What is the mean concentration or the average concentration of PSA for men who are at risk for prostate cancer? Then what do I ask? I ask for an estimation of a mean. What is the random variable? That's how you have to start. What's the random variable? The random variable is X. What is X here? What? PSA concentration in a male patient at risk, at high risk for prostate cancer. Okay? What? No. The study is the study. Now, you do statistics because you want to extrapolate. If you say, I stay in the study, you don't need to do any statistics. Everything is right there. You do statistics to extrapolate information that actually is pertinent to the more general population. Otherwise, if you stay within the study, you did the census within the study. You have no clues what's happening outside of your study group. You do the study to find some values for the general population, for example, to have a guideline. Okay? So, what do we have to identify here? How do we have to think? What problem do we have? We have a confidence interval. We want to estimate a mean. So we have a confidence interval estimation for a mean, correct? So that's how we should proceed then. We have confidence interval estimation for a mean. Confidence interval estimation for a mean. For the mean of X, where X is male patients with or at high risk for prostate cancer. PSA concentration of male patients, at high risk for prostate cancer. Now, when you look at a study, this statement, high risk for prostate cancer, should be clearly identified. Because if it's not clearly identified, and that's what studies actually do, if you look at them before they present their data, they identify how they define the high risk for prostate cancer. They did something else. They did some examination, like an ultrasound or a dactyloscopic examination through the rectum. Typically, they do both. So, we have this. Now, how do I estimate the mean of X? The first thing I have to look at is what? My sample size. Because when we estimate the mean, we use the central limit theorem. The central limit theorem is distribution agnostic. So we don't have to assume necessarily that X is normally distributed. So here we have a sample size which consists of 296 patients. And when the number of the sample size is greater than 30, you can abandon any assumptions about, you don't need actually any assumptions about the distribution of X. So the next step is N is greater than 30. Here N is 296. So we do not need any assumptions for the distribution of X. If N is less than 30, then we actually need to do some assumptions for the distribution of X. Here we don't. Now, of course, we assume that the sample is random. So we assume that whoever did the study took care of independence, has identified a population that is a subset of the population, the sample, namely that is homogeneous. It's exactly the same, a good extract, a representative sample of the entire population, or which will describe X, our random variable. So we make these assumptions by default. Okay? And after we have made these assumptions by default, now we can estimate the mean of X. You have a fairly big sample size. So I will do an estimation. I want a 99% confidence for this problem. Let's try to find the 99% confidence interval. What is this confidence interval for the mean of X? The mean of X will be between X bar minus, what distribution do I use? Standard normal, okay, Z. So my critical point here will be Z of alpha over 2. What is alpha? I want 99% confidence, so what is alpha? 0.01, okay? So if you use the standard normal distribution, so now you have to find your critical points. That bulk here will be the 0.99. So you divide the 0.01 which is left, that should be the sum of this area and this other area. Those black areas that I have actually I'm showing here are called critical areas. What is the size of each one of them? 0.005, correct? So here the area is 0.005. So what should be this point, which is the Z of 0.005? How do I find it? I go to the tables and I look for what point, what percentage point actually there. Those are points that we'll identify by looking at the normal distribution. So this is the point, the point that I want to find out is the point Z, such that if you plug it in, the distribution function of the standard normal distribution, it will give probability equal to 0.995, which is 1 minus the 0.005. Okay, which is the point? Which is this point? You look up the table. And actually, you can even go here to the bottom of the table on page 569. It says, selected upper percentage points. You want the percentage points which corresponds to 0.995, or to, here it has tail probability. Now, this here, the area, which I said it's equal to 0.005, is called tail probability because in the PDF of the distribution, this is the left tail and this is the right tail. And we call them tails because they fall down, like the tail of an animal falls down, hangs. Okay? Unless the puppy is happy and the tail is up, and well, that's why we call them tails. So what is, if you look here, 0.005, you will find the upper percentage point, this is 2.57576. So this point that you're looking here is 2.576. So I will have this times, what do I put here? Let's go to our book, our data set. What is this number here, 17.05? It says standard deviation here, but what is this point? What kind of standard deviation is this? Huh? It's the sample standard deviation, that's the S. So if we go back to our problem, here we have S equal to 17.05. The sample average, X bar, let me copy it, again is 8.79. All right? So that's the sample standard deviation, the one that I'm given here. By what I know, what should I put here? What do I actually need when I construct the confidence interval? I need the true standard deviation. And here I will divide by the square root of n. What is the square root of n? Well, it's the square root of 296. That's the lower bound. Here's the upper bound. We will plug in all those numbers now. So that's my confidence interval. Now, what do I do with the standard deviation here? The standard deviation of x, what can I do? The sample size is greater than 30, and even more, it's greater than 50. So since the sample size is 296 and it's greater than 50, we can replace, it's called very big sample. That's the case where we call the sample very big. We can replace the unknown standard deviation with the sample standard deviation in our case. So after we do all of these things, what is our confidence interval? It's 8.79, our 99% confidence interval, minus 2.576 times 17.05 divided by the square root of 296. That's our confidence interval for the mean. And that's the end of the problem that I solved. Yes. Is it clear? So here, what did I do? I have a fairly big sample, so I don't care about the distribution of x, since I'm looking for a mean. I based my conclusion on the central limit theorem. Yes. Yes, it's a plus here, yeah. It meant to be a plus always. I base my assumption on the fact that my conclusions on the fact that I have a fairly big sample. The sample is greater than 30, so I don't need to make any assumptions on the distribution of x. I use the central limit theorem. That's why I don't need to make any assumptions for the distribution of x. And furthermore, I can replace the unknown standard deviation of x with the sample standard deviation which I have from the data, because the sample size is very big, is greater than 50. I can do that when the sample size is very big. Now, what is very big and what is less than very big is a matter of personal interpretation. I follow the safe approach to say that a very big sample is a sample which is greater than 50. Other authors say that it's still when the sample size is greater than 30, you can replace the unknown standard deviation of the population with the sample standard deviation. I tend to stay on the safer side because when you do this replacement, you need to be able to have a good sample size to allow you to see all the variability in the population. Otherwise, you will underestimate the sample standard deviation. Yes. You will do it, but you have to say that these results, look, you always, when you get numbers, you always have to you crunch your numbers and derive something. But you can say that this estimation may suffer from the fact that the sample size is not very big, and since I'm not given the sample standard deviation, I cannot very easily conclude about the data. Yeah, so the confidence may not be the nominal confidence overall. You may have a lesser confidence on that interval. Yes?
Well, you pretty much said it's the same process, but you just put like an asterisk. It may not be
yeah, there's an asterisk there. Look, I may have missed something. Okay, I did my work as best as I could, but what can I do? That's the data I was able to recruit, the data I was able to find. Well, if you have a fairly small sample, then, and that's those are other cases, where if you have very small samples below 30, then you need to make assumptions about the distribution of X. So if the sample size, if n is less than 30, then X must be normally distributed. And when X is normally distributed, so that's the necessary assumption, then must assume, let's say. Now, the X will never have normal distribution precisely. There is no such thing as precision in statistics. You make that technical assumption, but you need to justify this assumption a little bit. So you take your data. The formal justification for the data is to do a so-called normal plot. So to justify that X has normal distribution, you need the so-called normal plot. What is the normal plot? The normal plot is a QQ plot, is a quantile to quantile plot, when the benchmarking distribution is normal distribution. And there is a way to be done. I don't really, I'm not going to ask you to learn to produce QQ plots in the exam, because those are complicated. And even if you have 15 or 16 data points, it will take time. Calculators do that very quickly, and they give you actually confidence on whether the data come from a normal distribution or not. These are other types of tests that actually perform this assessment. What you can do, though, which is quite quick, is to do a box plot. So if you do the box plot, then what would you be looking in order to assess that you have a normal distribution? If this is your box plot, you will be looking that your median is pretty much between Q1 and Q3. You don't want to see the median to be very close to that Q3 or to the Q1. That's the first quartile, that's the third quartile. So you want the median to stay roughly somewhere in between here. Then you can assume that the data are approximately normally distributed, and then you can proceed to use the so-called low sample size approach for the estimation of the mean, and then instead of the Z, you use the so-called T distribution, and that is done in such a way that you are allowed to use the mean. Okay, so what would be the interval in this T distribution? Let me give you the confidence interval. Now the confidence interval using the T distribution would be X bar minus T. The T distribution is called student's distribution. I will tell you the story why it's called student's distribution. And it has two parameters. Alpha over 2 the level of significance divided by 2, and this n minus 1, which is called degree of freedom. And it's a term that comes from physics. Here, precisely, you are allowed to replace the unknown sigma with a sample standard deviation, and you divide by n, by the square root of n. So, what are those degrees of freedom? Now, and what is student distribution? Students distribution was invented by William Gosset, who was working actually at a brewery, one of the biggest breweries, still is one of the biggest breweries in the world, in Ireland. Now I forgot the brewery. Guinness. And we was based in Dublin, and he wanted to do a quality assessment, namely, when you buy a bottle property, the tails of the student, it looks like this. It looks like it's bell-shaped like the normal distribution, but the decay of the tails, the rate at which the tails fall down to the horizontal axis is not as fast as that of the normal distribution. So that allows us to do more accurate calculations when we have small samples. But the necessary assumption is that the random variable is normally distributed. That has to be interpreted with some freedom. And since you cannot do a QQ plot for normal distribution, in a formal study we would do that. We would basically put the data in the computer and come up with a normal plot, which is a QQ plot for the normal distribution. And we would actually get an assessment of how confident we are that the data come from a normal distribution. Since you can't do that, just do the box plot. And observe, the test for you would be where the mean is sitting. Not the mean, the median, what I call M, where that bar is sitting. If it's seated close, not close to the middle, but it's very close to Q1 or Q3, then you don't have a normal distribution, and therefore you cannot proceed with that test. Okay? Or if you proceed with that test, then you have to put the asterisk that the data do not appear to come from a normal distribution. However, we assume that they come from a normal distribution, so our results have to be used with caution, are not super reliable. And in this case, what do? We just go and get more sample, a bigger sample size. We get more data. That's what we have to do if the data cannot be manipulated. But the advantage of this is that you don't have an unknown quantity here. You have the sample standard deviation, S, directly plugged in. Okay? So let's see if we can do a problem with this. Okay? So if you look here, I have some groups. That's again sample standard deviation. It's identified in the table with a stupid name. Deviation from group mean. But that's again sample standard deviation. So if you look at number 10, the entire group is n equal to 301. If you look at 10 people, sample size here of 10, you see how smaller the data is. That's actually very important, because here you see that if you work with the entire group, you will be fairly close. Look at our calculations that we did before. This is the mean. So since you have 296 is roughly what? It's about 256 is square root of 256 is about 16. It's 16. So when you have then you have a concentration. If you do the calculation, roughly the calculation here, you will have a concentration which is between 6.2 and 10 point something, between, let's say, 6 and 10.5. That would be the PSA.
6.24 and
11.34. Thank you. So you see, the 99% confidence interval is big, but it's 99% confident. So you still have the variability to deal with. If you look here, 6.8, if you take a sample of 10, a random sample of 10 among these people, it gives you a very small number. And that's exactly what I was talking about. If you have a small sample, chances are that you can't see the entire variability in the population. So you need to go to a bigger sample. Do the data come from a normal distribution? Yeah. I would believe that they come from a normal, perhaps they come from a normal distribution. But in this case, you would have very big uncertainty. So let's use the sample size of 10 here, which is fairly small. Now I need to use the assumption that the concentration of PSA in people who are in men who are at high risk for prostate cancer is normally distributed. And let's try to solve the problem with this. So I have mean PSA level 6.8 and standard deviation 2.0, sample standard deviation 2.0. And let's solve the problem here. So in this case, we would have 6.8 minus, let's look at that now. I will do a 99% confidence interval, so T will be 0.005. I do a 99% confidence interval because I did the 99% confidence interval before. How many are the degrees of freedom? The degrees of freedom are n, sample size minus 1. I have a 10 items, 10 individuals, my sample size, so I have 9 degrees of freedom. Is it clear? Let's now go and find this number. So we look at the next table here, which is the next page, which is table C6. And here you only have critical values. This is exactly what I want. I want the critical value for alpha equal to 0.005. So I'm looking at the very last column of the table in the book. For R are the degrees of freedom, so look at equal at 9, and this will be 3.25. So you look at the big multiplier, 3.25. And then my thing will be S is 2, and here I have the square root of 10 in the denominator, and I have 6.8 plus 3.25, 2 times the square root of 10. So what is this interval now for the mean? Let's see this interval, let's compare it with the interval we calculated before.
So even though the sample standard deviation is negative,
No, that was departure from the mean. So he uses the sample standard deviation. Okay, we can also use the other sample standard deviation we had before. But in this was 2 point, in this group, when you want a certain error. Now, this quantity here that I have outlined, this is called the sampling error, essentially. That's what you see reported in the TV. This one here, this quantity is called standard error of estimation. That quantity is called standard error of estimation. Essentially, it's the error, it's the variance or the sample standard deviation of X bar. If X bar has normal distribution, that's what it's going to be. And now, if I want to find the sample size so that the sampling error stays under control, sampling error stays less than E, then what is the sampling error? The sampling error is all of this quantity that I have here. So essentially, I have to find out what is N so that all of this thing stays under E. So let's do it with a Z first. Suppose that I had that, and I have my sample standard deviation, and I have N. And I want this to be less than E. Okay, here, when you do the sigma, actually let me go with the sigma here. You want to do the sample size. So there's no point to have sample standard deviation here. Because if you have not calculated, if you have not collected the sample, how do you know the sample standard deviation? First you have to collect the data, then you calculate the sample standard deviation. So you need an idea of what sigma is going to be, of the size of the sigma. And that you can get from different data, or you can actually use certain rules of thumb for this particular case. And once you do this, then you solve this inequality with respect to N, so you will have this. And if you take the square here, then of course that eliminates the square root, and it gives you a floor, a lower bound for N. So you take a number, you take N to be greater than this number. Of course, N has to be positive. So let's see if we can identify a problem to solve for this particular case. Find the sample size. And I'll take an example from the book, example 4.2, on page 229. The process used to manufacture paint yields on the average 7 tons of paint each day. Yields, however, vary from day to day due to changes in raw materials and plant conditions. Suppose that it is fairly well established that the daily yields are normally distributed and that the variability from one day to another is more or less independent, and that the standard deviation is 3 tons. Find what is the 95%, what sample size do we need in order to have the 90% confidence that our estimate of the average production of paint is estimated within 1 ton. So here, in this particular problem, we need E not to exceed 1 ton. So we'll essentially take E to be equal to 1 ton. 1 ton of paint. and we make a we make a judgment for sigma. That judgment does not have to be accurate. You can make it bigger. You can pick a value for sigma that allows you to feel safe for sigma, but do not underestimate. You better overestimate sigma, meaning that you take a bigger than what it actually is. That won't harm you. It will simply force you to take a bigger sample. But you can take sigma big. Don't take sigma small and lose variability. So here in this problem, they take sigma to be 3 tons. And they want 95% confidence. So what shall I do here? I will take what should be the alpha that corresponds to 95% confidence. It's 0.05. So alpha over 2 will be 0.025. And now if we go to the table to find z of 0.025, what that value will be, let's go back to table C4 on page 569. We'll find that what corresponds, the z, the upper percentage point for 2.5%, that's what this upper percentage point is 1.96. So this point that I have here essentially cuts from the standard normal distribution and make a better standard. I know what's the problem is. Yeah. So it's this point, so that this area here is 0.025, so all the remaining area is 0.975. So this is exactly the 97.5 percentile, 1.96, for the standard normal distribution. Okay? That's what this point is. So if I want to do this calculation now, what that would be? I would have 1.96 for the sample size, sigma is taken to be 3, E is taken to be 1, that will be less than the square root of n. So essentially it's 3.96, that's basically 6, let's say 6. X should be the square root of n but less than 6, so n should be greater than 36. So the minimum sample size I would take is 36. All right? Here, of course, I do assume either normal distribution. If I cannot assume normal distribution, what else should I say? When I try to estimate n. If you don't assume that you have a normal distribution, then you cannot accept a value of n that is less than 30. Why? Because then you use the standard limit, the central limit theorem, which tells you that you have to go to a sample size greater than 30 in order to be distribution agnostic. So you have an extra constraint when you do this calculation. So consider n greater than 30 if you cannot assume that x is normally distributed. Okay, we'll stop here. I'll do a few problems next time, but I will assign you some problems to work on. And next time we will, I also want you to consider to do proportions. Watch the video for proportions, and also watch the video for...
Actually, I turned it in on. Turn it on.
My medical book. It's Here I have a study which actually does the following. Let's read the story a little bit. Femoral neck stress fractures occur in young people engaged in sports, combat training, and other similar activities. And those are very difficult to cure fractures. And they can, you see that it leaves the patient somewhat impaired. And therefore, one potential risk for these kinds of fractures is bone density. And now there is in this example, there is a very big study of bone density measures. The University of California, San Francisco norm has been established based on this study. But for what we're interested in, to find what kind of risk factors we have for people with femoral neck stress fractures, we use a study which is basically compiled by data received from 18 people, 18 patients. And notice that I'm using the word people. People means male and female. And as you see here, in this database, in this small extract of data, that study is small, you have 3 females and the remaining 15 are male patients. Here we have their bone density, and I want to calculate the average bone density of these people. In other words, if I have now the random variable, X is bone density of patients with femoral neck fracture. I hope I didn't misinterpret the data. Norms do people. Bone density was measured with, okay, so all these 18 people had femoral neck stress fractures. So I'm okay the way I'm defining my random variable. Now the question is, estimate the mean of this random variable X. Now, since we have 18 patients only, and 18 is less than 30, we work with a small sample. So the necessary assumption in order to be able to continue with this, to use the data in a reliable fashion, would be to be able to assume that X has approximately normal distribution. Or, well, precisely it's not going to be, but we have to see some evidence there that X is normally distributed. Because sample size is equal to 18, which is less than 30. Now, that is something we want. It doesn't mean that it happens. So we need to check whether this thing is happening, and in order to do that, I will do, as you would do in class, do a box plot. So now I take the data, the bone density that we have here in this table. Here, that's the column where you see the bone density. Take the bone density from both female and male patients, because we're talking about people. So people are males and females. You cannot preclude the females, although you have a smaller number of them. Ideally, you would like to have more, but anyway, you can't force people to have these kinds of fractures because you want to collect the data. You just simply have to chase more data. And that's the column, those are the values, the bone density values in milligrams per milliliter of calcium actually. that I'm measuring, and I will order these data points in ascending order. So if I order them in ascending order, here are the data points. So here I have the list of the data in these 3 lines, the data from the 18 patients, their bone density in ascending order. And now I can construct a box plot. To construct the box plot, I have to find the first quartile, the second quartile or median, and the third quartile. What is the first quartile? The first quartile is the number which divides the lower 25% of the data from the upper 75% of the data. So actually divides. That's what the first quartile does. You can watch the video on the quartiles, but you can actually also see it in the book. It's on, you can see the quartiles introduced in page 29 to 31. This list, although it has only 18 numbers, takes a little bit longer to do so. It's a very convenient way if you intend to do quartiles to essentially begin a stem and leaf representation. So let's see here what would be the first quartile. The lower, if you multiply, you have 18 data points. 18 times 25 over 100, which is 1/4, will give you 4.5. So you need a number between the 4th and the 5th. Actually, you need a number which essentially will be the 4.5 number in that order that would divide the lower part, the lower 25% of the data. Now, this number should be rounded up to 5, and if you see 1, 2, 3, 4, 5, this, if you take 140.1, then what is being left of 1, what is on the left, what the numbers that are, the data points that are less than 140.1 are 1, 2, 3, 4. And the numbers that are higher are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So you have 13 numbers that are higher than that, and essentially if you divide 13 by 18, numbers are immediately exact, it's practically 72%. So indeed this number divides the lower 25% of the data from the upper 75% of the data. So I designate this number as the first quartile. Now, in case that 18 times 1/4 that I have here wouldn't be actually equal to a non-integer number, but would round to an integer number, I would have taken the number which is actually bigger. I would have taken, suppose that this number was 4 and not 5. Let's see what would happen if this was 4 and not 5. Then this number, that's not of course correct, but suppose that we have a number that gives 4, that would be like 16 data points. Then the first quartile wouldn't be the 4th number, the 4th data point, but it would be the midpoint between the 4th and the 5th. So this is exactly how we get the quartiles. Now, let's apply this process to get the second quartile, or the median. So this is the median here. The median divides the lower 50% from the upper 50% of the data. So here you have 18 points. So you have 9 which are lower 50% and 9 that are higher than 50%. So let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. So you get this number here. This is the 9th data point, and this is the 10th data point. On the right of a hypothetical number which is between these two, you have 1, 2, 3, 4, 5, 6, 7, 8, 9. Of course, 9 data points. So what would I designate naturally as the median here? Well, the midpoint between the 9th and the 10th value, and that actually ends up being, according to my calculations, 154.1. So that's the median. And likewise, if you take the third quartile, this is 164.9, because if you take this number here, you see that you have 1, 2, 3, 4, and on the right of this point, you have 1, 2, 3, 4. Therefore, this is the third quartile here. Let me just try this. Let me show you that I can do some calligraphy. And likewise, you have the third quartile. So now let me plot the block and whisker, the box plot or the box and whisker plot. On the very left hand, I have the lowest value, 97.3, and on the right, I have the 199.0, the highest value. Now you have to put everything else in perspective according to the distance that you have designated between the maximum and the minimum. And if I do the job right, it will be approximately, right? It will not be perfect. I will put my Q1 here. That would be my 140.1. My median and my third quartile will be 164.9. That's my third quartile. Now I design my box, and now I put the median, which is, as you see, slightly to the right of this, of the midpoint between Q1 and Q3. So this is the median, and it's 154.1, as we have discovered already. Okay. So that's our median here. Now, the midpoint between Q1 and Q2 would be somewhere here, and that would be exactly 152, something like that. And if you see that difference between the midpoint and the median, it's just only roughly 2 points, and the distance between Q1 and Q3 is quite significant. It's about 24 points, so 2 divided by 24 essentially is 1/12. So it's negligible. The difference between the median and the midpoint between Q1 and Q3 is negligible, and therefore I would say that the data appear to be normally distributed. So X appears to have normal distribution. Now, if you really want to do this right, you have to use the Q2 plot, which is with respect to the normal distribution, which is called normal plot. But I'm not going to ask you for something like this. I'm going to ask you for an argument like this particular one that I presented. Therefore, we can use the t-test. the t statistic actually, the t statistic, student statistic to estimate the mean. Of course, one standard assumption, the mean of x, okay? One standard assumption is that the sample is random, so you have the independence, you have identical distribution in all of these, identical in all of these 18 measurements, actually identical to x. You believe that all these things have been taken care of, and the only thing that you actually have to check is that x is normally distributed because you have a small sample and you need to employ the t-test in order to give some credibility to your results, sufficient credibility actually to your results. Now, what do you need to compute the t-statistic? Well, an essential calculation uses the sample standard deviation, S. Sample standard deviation. And to calculate the sample standard deviation, you take the sample variance, which is S squared. And the sample variance is defined as almost the average, 1 over n minus 1, where n is the sample size, of x by the ith data point that you have minus x bar squared. This is the sample average. And this is one of the data points, the ith data point, for example, the first one that I had here for I equal to 1, that would be, if I go a bit up, roll this up, that would be 139.6. That would be x sub 1, the value of x sub 1. This is exactly, as we call, a realization of the random variable, which is bone density in patients who have this femoral neck stress fracture. A second value, a second realization, returned the value 167.2 in bone density, and so forth and so on. So assume that all of these have been collected independently of one another, and all of them are representing this population. The bone density of people which fall into this particular category of patients. And now this is a kind of complicated formula, so I'm going to give you here a shortcut to calculate the sample variance because you will need it. And here is the shortcut for the sample variance. Numerator, n times the sum of the x sub I squared. So you take the x sub i's, you square them, and you take the sum of these squares. Minus the sum of the x sub i's, which you already need in order to calculate the sample average. Square this quantity again, and divide this difference by n times n minus 1. Take the square root of the sample variance, and then you have the sample standard deviation. Now, this is nicely done with Excel to calculate this. And this is what I'm going to do to complete that particular calculation. So here I constructed my small Excel file. I put the bone densities here in the order that it's ascending 1 through 18. And here is the sum of all of them on the 19th column and on column B, on the 19th row actually. And on column B I have the square of these values, of the values that I have in column A. And this is the sum of the squares, B19. So here I do, actually there is also a function which is already prepared in Excel, a statistical function which is called standard deviation. That's sample standard deviation, you can use it. But you can actually, I did my own one, just to be sure that I'm doing it right. Being a classical mathematician, I sometimes prefer to do things not with built-in libraries, but with bare brute force. So this is the sample variance, 576.4 and 24.0. That's what I'm going to use, 24.0, because all the densities are given with one decimal point, so I will just round to the first decimal point. That's my sample standard deviation. So now my actual formula would be the following. I take T, my statistic, which will give me the the confidence interval that I will take is now given by the T statistic, and this is going to be X bar minus T. Suppose that I want to do a 95% confidence interval. I forgot to mention the confidence before, but suppose that we want to do that. 95% confidence, that means that this alpha parameter is 0.05. So here we have 0.025. We have 17 degrees of freedom. This thing is acting on me. We have 17 degrees of freedom. And now we multiply up here with the sample standard deviation, which is 24. Just divided by the square root of the sample size. And here we have again X bar plus So let's see the interval. As we mentioned before, our sample, and now we need the sample average. So the sample average would be 276 divided by 18. So let's calculate it somewhere here. We need the function. So we need the keyboard again, equals A19 divided by 18. Boom. 154.2. That's the sample average. So I'm going back to my notes. 154.2 minus. Let's see what is this critical value. We look at the tables, and to find these critical values, when we look at the tables, you have 17 degrees of freedom, and you have 0.025, so that would be, you're looking for the 0.025 critical value, that would be 2.11. So this is 2.11 times 24 divided by the square root of 18, and plus 2.11, 24 divided by the square root of 18. Let's see what is the square root of 18, and let's finish the calculations. 18 square root is 4.24. And if you complete this calculation, you have found now the confidence interval, the 95% confidence interval for the bone density with patients who have suffered a femoral neck stress fracture. Okay, so that completes this particular exercise. Now I want to make a remark. So when I say 95% confidence, what does that mean? It means that in average, So what does that mean, 95% confidence? It means that, that in average, when you have well collected, correct samples of the same size, n, all of them, here was 18, of the values of the random variable that you study, 95% of the 95 times out of 100 times, out of 100 intervals, in 95 of them, out of 100 by which you don't know which 95, out of 100, the value of the mean of the random variable will be inside those 95 confidence intervals. But you don't know which ones are the ones from which you have collected. In other words, you may do everything right and still get the wrong value, get the wrong estimation. But what is the probability for this wrong estimation? Well, it goes down to 5%. And that's exactly is measured by alpha, and this is the meaning of alpha. It's trying to create a boundary, an upper boundary of the level of uncertainty when you carry out this procedure. But of course, that procedure assumes that the sampling has been done right. In other words, that you have, no matter how many you have a representative sample from the targeted population, here are the values of X, and the collection of the data has been done with independence. In other words, you cannot get all the people from all of your patients who have these stress neck, femoral neck stress fractures. You can just not go all and get all the data from the same athletic team, because over there you have correlation. You don't have independence because all of your patients would belong, or significant some number of your patients would belong to the same athletic team. You have to vary the athletic teams, you have to vary the locations, you have to vary also the gender. That's why we took male and female. Now, I would like to invite you to do the same problem, where instead now of X, the way I define X, you define X to be the bone density of male patients with femoral neck fracture, and estimate the mean of this new random variable X. Pretty much, you have to exclude 3 data points, and you carry out the same procedure. It should be easy to do that. Now I would like to the final sort of project here that I would like you to do. Look, actually observe the website that I'm using. It's wiki. I'll copy that so you can see it more easily, and I'll copy it here. And this can I want to zoom in essentially, but I think now you can see the data point, the data set. You go to wikistat.ucla.edu and then /soccer, SOCR, /index, and then you will be in this data set. Normal, and I'm interested to go to the neuroimaging data sets, and let's look normal and schizophrenia children neuroimaging study. Now we go to this study, and let's look at the overview of the study. This is a neuroimaging study where the brain has been segmented to various areas of anatomical significance and physiological significance. And as you see here with the colors as they appear in this particular image, this visualization, and they want to see if certain of these, the size of certain areas after the segmentation that is done can be predictors of schizophrenia. And actually this segmentation tool measures several things, several variables, total brain volume in voxels, and then you can change that to cubic millimeters, total gray matter volume, total white matter volume, total cerebrospinal fluid, which can be measured. This is actually outside of the brain, and with MRI we can see it very easily. These are MRI data. And they want to see those, essentially those predictors. Now, we want to compare, and we know actually the range for the acceptable the acceptable ranges for the people who are normal. And here are the data. So you see this data set is fairly big. It's kind of typical of what a biomedical study would look like. On the left column, we have the subject, and the subject is identified with a number, and that is done to protect the privacy of the individual who participates in the study. And then we have the so-called categorical variables. Sex is one categorical variable where we have a data where the teenager is male or female. Here you have the values, and all of these are the numerical data from that column on all the way to the right that might be of interest. You see many variables here. You can play around with it as much as you want, but I don't want to do a lot of things here. I just want to illustrate a point, to illustrate a problem that you can actually do, and I hope that it won't be way too difficult to actually evaluate. So here we have many individuals. I didn't count how many individuals we have, but let me do that. And now I would like, if you count, you have about 50 or 60 individuals. I don't know, but this is, I don't think, I tried to count it, but I think I lost the count, but it's definitely the number of subjects that you have is over 30. So you have a lot of data, a sufficient number of data points. And what I would like you to do is to go ahead and calculate and take as random variable the cerebrospinal fluid measured in cubic centimeters. Here it's measured in cubic millimeters if we see the analysis of the data set description. I guess you know how to transfer cubic millimeters to cubic centimeters and vice versa, so I'm not going to go through that, because if we have to go through that, then I think you will make me mad. You can find it out. So if X, and let me go to my file, here's my file. So study, schizophrenia study. I spell schizophrenically, schizophrenia in teenagers, in adolescents. That's the study. You go find the study, you've already seen the, and you will see it again, the precise link. So I have a random variable which I call CSF, which is volume of cerebrospinal fluid in cubic millimeters. I stress that because you need to have the units right. We have n greater actually than 50 here. You have a fairly big sample size, so you don't have any problems in doing your estimations. I would like you to estimate the mean of this random variable, which I denoted now in a non-conventional way, CSF. I don't want to give it a name like XY. I just call it CSF, so you don't forget that this is cerebrospinal fluid. So I want you to estimate the mean of it, the mean of this random variable. Do you need to do a box plot? The short answer is no. You don't need to do a box plot for this particular one because the sample size is fairly big. Do you need what is the statistic that you will use? Well, here use the z statistic, the standard normal distribution. Exactly, more precisely, more accurately, you use the central limit theorem to do your estimation. Do you know sigma? Of course, no. It's unknown. But since you have a fairly big sample size, greater than 50, replace it with a sample standard deviation. So you can proceed. Here is the sample, the data set once more, and you can actually see the data set that I'm using. You see the link, SOCR datasets, normal and schizophrenia neuroimaging study of children. It's SOCR, that's the dataset collection that we have. And actually you can compare what is the confidence interval that you will find a 95% confidence interval, then find a 99% confidence interval, and compare it with confidence intervals for F and compare them with normal ranges for CSF, derive conclusions, derive your conclusions. Okay, so this is the, and once again, which is the data, this is a problem, and this is actually an assignment for you to turn in, and I will, in the announcement, post a number of points that this particular assignment would take. I walked you through the most important part, and since what I told you is that since you have a fairly big sample size, you don't need actually to make any assumptions about the distribution of the random variable CSF. You simply have to do the job. Similarly, you can calculate confidence interval for other random variables that are in this data set. Here again, here once more is the data set. I'll put it. So here is all the data that you actually need to do this, to solve this problem. Okay, so with this, I'm going to show you the data set one more time. And the problem is estimate the mean of the random variable CSF, cerebrospinal fluid, volume in cubic millimeters. Thank you very much, and I hope that you enjoyed it.